Well, howdy there, Geometry Fabulousness. Welcome to another episode of your favorite class. I know, I know. It's okay. It's okay to like math. It's okay. Um, Here's a warm-up for you. Let's pause the video, kind of think about this, see if you can wrap your head around it, and then start the video back up, and I will help you out with it. Go. Alrighty. So this problem comes from some work that we did with perpendicular bisectors. And so a strategy with solving problems like this is to draw the figure and label the sides from the problem. And then that will open up visually what's going on in this problem. And you might have a moment where you're like, oh, okay. And hopefully that'll happen. So let's kind of pull this together. So it says find Wx, and so I'm going to mark that. Wx is what we're trying to find. We're trying to find this little distance right here, Wx. When Wz equals 20, so Wz, this one over here, is 20. Wy, so this entire distance from W to Y is 14. Let's do it like that. And YZ is 20. So we know a lot about this figure now. We know that the distance between WZ and ZY are exactly the same. And we have the converse of the perpendicular bisector theorem, which says if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. The perpendicular bisector of the segment. So that's some significant information, and that theorem pulls everything together. If we know that WZ and ZY are the same, and we know that the whole distance from W to Y is 14, the converse to the perpendicular bisector theorem tells us the rest. If a point is equidistant from the endpoints of a segment, then that point is on the perpendicular bisector of that segment. Well, now that we know that the distance between Wx and xy has to be the same because of that theorem, then we know that Wx has got to be half of 14. And so Wx must equal 7. And there you go. So your strategy in geometry problems is to take all the information that you know, combine it with a fact in the form of a theorem or a postulate, and help that take that last step. So in this one, we labeled the figure first, and then we kind of talked through that theorem to give us that last piece. And I'm not saying this stuff comes easy. I'm just saying that with practice, you can really see how these theorems inform how you're going to solve these problems. It's kind of a whole other way of thinking than you might have done before. So it's okay if it takes you a little while and it's a little bit difficult. But what's going to make that difficulty go away is trusting yourself and trying. All right, here we go. So now's a good time to update that notebook. The last time you watched a video, it was perpendicular bisectors, and so you probably have an impartial set of notes for perpendicular bisectors. You have a page that kind of looks like this, and you have notes here. And it's perpendicular bisectors is the topic, and then you have the essential question, the EQ right there. And what you don't have now are questions, and that's what you're going to do now. When I say pause the video and write questions for your last set of notes, that's what you're going to do in this column. And in this column, you're going to be writing questions that are answerable by the notes that are right next to it. So say it says, you know, definition of perpendicular bisector right here, your question might be, what is a perpendicular bisector, over on that other column. Once you get that done, you might go back to some previous notes and write a summary. Don't write a summary on this one yet, just because, you know, it's not time. You want to review your notes on different days. I have no idea why it, well, there we go. But on a previous set of notes, write a summary. If you don't have a summary to write, then don't worry about it, because maybe you've done all of that already. And then get a page ready for today's notes, and that is going to include basically doing this right there. And that is how you get a page ready. All right, so the next thing is what goes here, the topic and the essential question. That's what's next. The topic today is angle bisectors, and the essential question is, what is true about a point on the bisector of an angle? Make sure that topic makes it into the table of contents of your notebook, please. Sorry, I had to pause it there for a second. Yeah. So you've got that whole thing set up, I hope, and let's move forward. So a quick reminder, we got a couple of theorems, the perpendicular bisector theorem and the converse of the perpendicular bisector theorem. I just want to remind you that they exist, and one says in a plane, if a point lies on the perpendicular bisector of a segment, then it is equidistant from the endpoints. And we've been talking about that for a couple of days now. And then it's converse. In a plane, if a point is equidistant from the endpoints of the segment, then it lies on the perpendicular bisector of the segment. We're going to take these two ideas and apply them to angles today, and talk about how we can understand the relationship of bisectors within angles. And that brings us to a couple of theorems, the angle bisector theorem and the converse of the angle bisector theorem. Now, an angle bisector is just like a segment bisector. It cuts the angle exactly in half, and that's what you see in this picture here. You see this ray, AD, and it has created congruent angles. That's what those markings mean. Those angles have exactly the same measure, and since that ray has created those congruencies, then that ray is an angle bisector. Now, what this theorem says is this: if you've got a point, say D, on the bisector of an angle, if a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. If a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. So if we're taking a look at this point D, and we recognize that it's on a ray that creates two congruent angles, in other words, it's an angle bisector, then we know D is equidistant from the two sides of the angle. So that means this distance between D and C and this distance between D and B are exactly the same. And so now we can tell things about how far away those are and about those right triangles that get created. When you're talking about distance between points and sides, it's always the perpendicular distance, the one segment that meets that side at a perpendicular angle or at a 90-degree angle. So that's important to note, that we're going to want to have right angles there. So we also have the converse of the angle bisector theorem, which just sort of flips this idea. If a point is equidistant, oops, wrong color, Miss Waite. Oh, sorry about that feedback. is equidistant from the two sides of an angle, then it is on, then it is on the angle bisector. If a point is equidistant from the two sides of an angle, then it is on the angle bisector. So if we know that the distance between B and D is exactly the same as the distance between C and D, then we also know from this theorem is that the ray AD is a bisector. So now we know that. So knowing these theorems tells us other things about these figures. So it's one thing to know a theorem, it's another thing to know how to use it. So that's what we're going to concentrate on. So what we're being asked to find is the measure of angle GFJ. So let's wrap our heads around it. GFJ. We want to find this angle right here, GFJ. Okay, well, let's look at the evidence that we have. We have a point, J, on some ray coming through this angle, this bigger angle, GFH. And we also know that J is equidistant, because 7 and 7 are the same, are equidistant from the sides of that angle. And the converse to the angle bisector theorem says that if a point is equidistant from the two sides of an angle, then it's on the angle bisector, which means that this angle must be the same as that one. Well, if that's true, and JFH is 42, then the measure of angle GFJ must also be 42 degrees. So take a look at the figure, take a look at the evidence that you have, and apply the theorem. If we have a point that's the same distance away from the sides, then we know that that point is on the angle bisector, which means that the two angles that are bisected are exactly the same, which means if one is 42, then so is the other. We can also use this to solve problems like this. Now let's take a look at what we have. So we have the angle bisector theorem that says if a point, right here, is on the bisector of an angle, notice how you have congruent angles, so that point is on the bisector, then it is equidistant from the two sides, which means that this distance is the same as that distance. If a point is on the bisector of an angle, then it is equidistant from the sides. So now that we've kind of talked our way through that theorem and used it to mark our figure, we can see that in order to find the length of RS, we're going to need to know x. And in order to know x, we need an equation. But the geometry of this problem, the theorem tells us that the distance between P and S is exactly the same as the distance between R and S. In other words, 5x has got to be the same as 6x minus 5. And now we can solve for x. I'm going to subtract 6x from both sides, because why not? It creates a clever cancellation. And I have 5x minus 6x, or negative 1x, or just negative x, equals negative 5 left on this side. Now if negative x equals negative 5, then positive x equals positive 5. And now I've found for x. Now I want to find the length of RS, but RS is 6x. Let's see. RS is 6x minus 5. So I just have to take that 5 and drop it in right here. RS is going to be 6 times 5 minus 5. Well, let's see, 6 times 5 is 5, 10, 15, 20, 25, 30. And then we got to remember to subtract 5. And so it looks like RS is 25. Now we could check that because what we know is that RS has to be the same as SP. So if we put a 5 in right here as well, and we ask ourselves, well, what is 5 times 5? Well, it's 25. And since we're getting the same number on both, we know we're right. So again, the process is take a look at this figure, see what you have. You have a point, S, on the angle bisector, that ray QS through that angle. If a point's on the bisector, then it's equidistant from the sides, which means that SP and SR have to be the same. And that leads you to the equation to solve the equation for X, plug X in, and finish the problem. All right, a couple more. So it says, we're going to use the same figure for both of these. It says BD bisects ABC. Let's start right there. Mark up this figure as we go. BD bisects ABC. Well, here's BD, and it bisects ABC, which means that this angle is congruent to that angle. That's what bisects mean. And DC equals 6. There we go. And what we want to find is DA. Well, we know that if a point is on the angle bisector, then it's equidistant from the two sides. And so if DC is 6, DA is also 6. Okay, let's do the other one. BD bisects ABC. So it's the same setup. Those are congruent. AD, this one here, is 3Z plus 7. And CD is 2Z plus 11. 2Z plus 11. Find CD. So we're trying to find this length here. Well, if we want to know that length, we're going to have to find the value of Z. In order to find the value of Z, we need an equation. In order to form an equation, we have to understand what the theorem is telling us. If a point is on the angle bisector, then it is equidistant from the sides. Well, if DC and DA are exactly the same, then 3Z plus 7 must equal 2Z plus 11, and now we can find for Z. I'm going to subtract 2Z from both sides. Creates that cancellation. 3Z's minus 2Z's is a single Z, plus 7 equals 11. Subtracting 7 from both sides gives us Z equals 7, 8, 9, 10, 11, 4. Great. And we want to find the length of CD, and we know that CD equals 2Z plus 11. We know that Z is 4, so that's going to equal 2 times 4 plus 11. And 2 times 4 is 8 plus 11, so it's going to be 19. CD equals 19. We can check it because we can also see that AD equals 3Z plus 7. Well, let's see. If Z is 4, then we should have 3 times 4 plus 7, or 12 plus 7, or 19. And since that's the same, we know we're correct. So again, the process is the same. Use the theorem to help you build the equation. Solve the equation for the variable. Plug the variable in to solve the problem itself. All right, here's one more, just kind of in the context of the real world. We've got a keeper, and the keeper's position relative to the ball and the goal posts forms congruent angles. In other words, this keeper is on this ray here, And what we have from the keeper's perspective are congruent angles there. Will the goalie or keeper have to move farther to block a shot toward the right goalpost or the left? In other words, if the keeper were to dive left or dive right, which one would be further? Well, let's think about this. The keeper ends up being a point, yeah, on the bisector of an angle, which would mean that the keeper is equidistant from the sides of that angle, which would mean that the keeper wouldn't have to move to the left or the right. It would be an equal distance from left to right. And so the question is, will the goalie have to move further to block a shot toward the right or to the left? And the answer is neither. Because the goalie is a point on the angle bisector, that goalie is equidistant from the sides of the angle and therefore will not have to move any further one direction or the other. It's a very fortunate place to be, actually, because you know, they have the best potential at that point to block that shot. All right, everybody. That's it. Angle bisectors was the topic. Your practice is on Big Ideas Math. The essential question, what is true about a point on the bisector of an angle? You might contemplate that and see if you're in good shape for being able to answer it. If not, come to office hours. Give me a chance to help you. All right, friends, have a wonderful day. Bye.